Alright, in this video I'm going to be doing some more series examples. I'm going to be doing some series that require the P-series test, the integral test, direct comparison, limit comparison. I'm sure there's something else. It's a lot of tests. Okay, so, and I'm also working BC Homework 11.2. So, for what values of P does the series converge? Okay, so, on A, I've got 1 plus 2 to the P plus 3 to the P plus ... plus, whoops, you can't even see that, that's n to the P and beyond. Okay, well, this is the sum of n to the P, okay? We know that the sum of 1 over n to the P converges when P is greater than 1. So maybe I could write this as a fraction, right? N starts at 1 and goes up to infinity. Okay, so we can put n in the denominator, it just makes the power negative, right? So it would be negative P. So I know that this would converge if the exponent of n in the denominator was greater than 1. So I'll say, all right, I know I need negative P greater than 1. So that gives me P less than negative 1. Okay, that makes sense, right? I would need it to be a negative exponent, so it would be in the denominator, and I would need that denominator exponent to be greater than 1. So yeah, P less than negative 1. All right, 1b is the sum from n equals 1 to infinity of 1 over n to the 2p minus 3. Okay. And this is going to converge, okay, we know, only when the exponent is bigger than 1. Okay. So I need that 2p minus 3 to be greater than 1. Okay. And so I'm going to add 3 to both sides, divide both sides by 2, and if p is greater than 2, then the series is going to converge. Okay. For C, I've got the sum from n equals 1 to infinity of 1 over n to the p squared minus 8p plus 13. Oh, okay. That was maybe a typo, but now I see what I'm supposed to do here. All right, I'm going to take that exponent and set it greater than 1 and solve. So I'll have, all right, p squared minus 8p plus 13. It's going to need to be greater than 1. Looks like this pen's running out. I'm going to subtract 1 from both sides. P squared minus 8p plus 12 is positive. That's the type of inequality we can solve in this class. This is factorable. So this is p minus 6 and p minus 2. Is positive, and we can't really do anything algebraically here, but we could make a sign chart, or we could make a sketch. I'm going to make a sketch. Okay, we know it's a parabola that opens up, and it's going to have zeros here at 2 and there at 6. Okay, so if I want to know where it's positive, I'm going to need p greater than 6 or p less than 2. For D, I've got 1 plus p squared plus p to the 3 plus p to the 4 all the way up to p to the n and beyond. All right, so 1 plus p squared plus 8. Okay, if we've got number to the nth power, that's a geometric series scenario. So I'm going to say, nice pens. That this is a geometric series with common ratio p, right? Each time I multiply by p. So this is okay, we know that for a geometric series to converge, the absolute value of its ratio needs to be less than 1. So I've got the absolute value of p is less than 1, and so that's just p between -1 and 1. Okay, 1 over n to the p plus n is one that I would have to use, if I had a specific value of p in order to show it converged, I would need to use the limit comparison test. But we know kind of the results of the limit comparison test is that if it's polynomial on top and polynomial on bottom, the difference in degrees needs to be bigger than 1 in order for that series to converge. Okay, so I really think that p is just going to need to be greater than 1 still. Let me think about that. If p is equal to 1, I have 1 over 2n, and that's going to diverge because it's half the harmonic, half of infinity, still infinity. And I think if n was bigger than 1, then this n wouldn't really contribute that much. Yeah, so I'm just going to say p needs to be greater than 1. That wasn't super exciting, but whatever. Make sure to pull up my work from last year and make sure that, no, it says p greater than 1 with no commentary. Yes, so that's just, yeah. Okay, and that's all for number 1. So number 2, use the integral test to determine if the series converges or diverges. All right, sum from n equals 1 to infinity of n e to the negative n. Okay, so I'm going to run the corresponding integral, right? I'm going to get a better pen to do that with, though. This pen will be all right. So I'm going to be integrating the integral from 1 to infinity. Okay, I could call it x over e to the x, but that's not going to really help me at all. I'm just going to call it x e to the negative x, and it's like, man, this is a product, but it's not going to be u du, so it must be u dd. Okay, ilate, algebra before exponential. So I'm going to let u equal x and dv equal e to the negative x dx, meaning that du is dx and v equals negative e to the negative x. Okay. And, all right, well, it's just going to equal uv, which is negative x e to the negative x. I'm going to have to evaluate that from 1 to infinity, minus the integral from 1 to infinity of v is, make that a plus, e to the negative x, du is dx. Okay, I'm going to need some more room here. This is like negative x over e to the x, and I'm interested in taking the limit of that as x goes to infinity. Minus, when I plug in 1, I'll have negative 1 over e. Okay, plus, and then now that limit is going to exist, so I feel like pretty good about this, but I don't know, maybe you don't remember if this is going to converge or diverge. We're going to find an antiderivative. That's negative e to the negative x from 1 to infinity. Now, this limit is 0 because e to the x grows much faster than negative x. So 0 plus 1 over e, okay, plus the limit as x approaches infinity of, okay, negative e to the negative x, that's like negative 1 over e to the x. Negative 1 over e to the 1. Okay, so this is equal to, you can't see that, but in total, okay, this again is going to 0 because it's e to the x is growing and 1 is not. Okay, but it ends up being 0 plus 1 over e plus another 1 over e equals 2 over e. This converges. Okay. Therefore, that series converges. Okay. So I would say, oh, also, I forgot to check the conditions, but, you know, so f of x equals x e to the negative x is continuous, it's positive, and it's decreasing. Okay, and since this converges, I'm going to conclude that the sum from 1 to infinity of n e to the negative n also converges. All right. 2b, they're going to ask for another integral test. This one requires a u/du substitution. Let's see. Yeah, 1 over n log n. This one is common enough that I just put it on the homework, and it's like, okay, hopefully you can remember that this one, I think this one's going to diverge. Yeah, and hopefully you just remember that. Don't have to run through the integral test every time, because that's kind of unfortunate. All right, so 2b is going to be the sum from n equals 2 to infinity of 1 over n times the log of n. Okay, log of n is always positive when n is greater than 2. Okay, greater than or equal to 2. It's really positive when n is greater than 1. This is always positive. Okay, the bigger n gets, the bigger these things get. So this function is continuous positive and decreasing for n greater than or equal to 2. I'm going to start off with that. I'm going to say f of x equals 1 over x times the log of x is continuous and positive and decreasing. We're going to consider the integral from 2 to infinity of 1 over x times the natural log of x, and maybe I'll write it like that, so it's maybe, all right, maybe I'll just rewrite it one more way in case you're watching this, you're like, I'm not sure how to anti-differentiate this. Okay, I'm going to write this as 1 over log x times 1 over x dx. Okay, maybe that would help. This is going to be, all right, the derivative of natural log of x is 1 over x. Okay, so I'm going to be set up for a really nice u substitution here, if you can just recognize that. So I'm going to let u equal natural log x. Okay, so that du is equal to 1 over x dx, which happens to be exactly what I have. Right? That's just going to become du. And I need to convert my bounds. Okay, when x equals 2, that gives me u equals the log 2. And as x approaches infinity, that gives me u is also approaching infinity, because we know that log has no limit as x approaches infinity. So I'm going to say this is now the integral from the log of 2 to infinity of 1 over u, 1 over log x, 1 over x dx is du. And so I'm going to find an antiderivative for 1 over u with respect to u. And I'm going to let u run from the natural log of 2 up to infinity. Right? We know that this is the limit as x approaches infinity of natural log of x minus the natural log of u when u is log of 2. Okay? This is a bad number, but it's just a number. And log of x as x goes to infinity, that also goes to infinity. So this integral diverges. And I'll say that, okay, since the integral diverges, I know the sum also diverges. I'm going to actually write on the document for this problem. For number 3, let's look at this. Consider the infinite series S, which is 1 plus a half plus a fifth, a tenth, a 17th, and a 26th, and 1 over 1 plus k squared. Probably going to do the integral test, right? 1 over 1 plus x squared, that's an antiderivative we need to know. Let Sn denote the nth partial sum of S. Sn in summation notation. Okay, the nth partial sum is where, okay, that's fine. is the sum from n equals 0 up. Well, I guess we're going to stop at n, so n can't be the index and the place that we stop. So I'm going to need a different indexing variable. And I'll say k. Is there? Yeah, sure, yeah. They were already using k as the indexing variable, so cool. So k is the index, and it's just like, a stand-in. And n is how far we're going of 1 over 1 plus k squared. Okay. And then we're going to determine whether S converges or diverges using the integral test. Okay, I don't really have an expression for an explicit formula for the nth partial sum that I can take the limit of, so I'm going to use the integral test. Okay, so f of x equals 1 over 1 plus x squared is continuous, positive, and decreasing. Okay. So I can run the integral test, and whatever the integral does is what the series is going to do. So I'm going to be adding from 0 to infinity the integral of 1 over 1 plus x squared dx. This is an antiderivative we need to know. We need to know that the antiderivative of 1 over 1 plus x squared with respect to x is inverse tangent of x. Okay. And then that's going to be the limit as x approaches infinity of arctangent of x minus arctangent of 0. Okay, I'm going to tell you arctangent of x is x goes to infinity, that's pi over 2. Arctangent of 0 is 0. So this in total is going to be pi divided by 2. And I guess if you need help with evaluating these values of inverse tangent, then just come talk to me before class next time, and I'd be happy to, discuss some trigonometry with you. Okay, and that's pi over 2, which converges. So since the integral from 0 to infinity of 1 over 1 plus x squared dx converges, we know that S converges also. Now we're going to verify the result from part B using the limit comparison test. I didn't think of that, and that would have been much easier. But I guess that's the point, that we're going to do all of that. All right. Next question's a good one. All right, using the limit comparison test. All right, so I'm going to make a decision on what I'm going to compare it to first. I'm going to compare this to 1 over n squared, okay, or 1 over k squared, right? The p series with p equals 2, which I know converges because p is bigger than 1. Okay, so I'm going to say the sum of 1 from p is a number that is bigger than 1. Okay, now I need to run the limit of the ratio of my series that I'm interested in to the one I know what's happening with, or the other way around. It really doesn't matter. Yes, that's supposed to be a k going to infinity of 1 over 1 plus k squared divided by 1 over k squared would be like multiplying by k squared over 1. And that limit, okay, it's same on top and bottom, just 1 power of k squared, so I divide the coefficients, and that's going to be 1. I'm going to say this limit is positive and finite. Okay. Therefore, since I know this one converges and the limit is positive and finite, I know that the other one converges by limit comparison. So from 0 to infinity, 1 over 1 plus k squared. Which is bigger, Sn or arctangent of n? All right, the nth partial sum is something that I could compare to the integral from 0 to n of 1 over 1 plus x squared. Okay, and I told you that the series is bigger. I told you that in the lesson. Like when we're doing the integral test, we're comparing the integral to the convergent series. Okay, if the integral converges, the series also converges, but we know that the series is bigger. Okay, so I know that that means that Sn is greater than inverse tangent of n. Okay, because the series is bigger. All right. Here's a question from 1974, BC number 4. Yeah. All right. If I'm going to do limit comparison on this one with 1 over the square root of k. Okay. I'm going to start with, hey, I know that the sum from 1 to infinity of 1 over square root k diverges by the p-series test. Okay. Then I'm going to compare the limit as k goes towards infinity of this thing, 1 over the square root of 3k plus 5 times, well, divided by 1 over the square root of k is like multiplying by the square root of k over 1. Okay, that's going to be, okay, if you can just see that this limit is 1 over the square root of 3, that's fine. If you don't believe me, I'm going to do some algebra here just to try to convince you. K approaches infinity of, all right, so I'm leaving that there. Well, I'm going to combine it into one fraction. But I'm going to factor out a 3 here. So I'm going to say that this is 3 times k plus 5/3. Okay, and if I'm taking the square root of the product, I can write that as the product of the square roots. So I'll do that. Root 3 times root k plus 5/3. And, okay, I think, these are essentially the same, and then I've got the 1 over the square root of 3 either way. Okay, I'm going to say that this is equal to 1 over the square root of is positive and finite. Okay, that's another way of saying is positive and finite is between infinity or 0 and infinity. Okay, so I'm going to conclude these two facts together give me that this series does right here. This series does the same thing as that one. So I'm going to say the sum from 1 to infinity of 1 over the square root of 3k plus 5 also diverges. All right, the next one's from 1980. Determine whether the series A defined below converges or diverges and justify your answer. Okay, so I'm saying bigger on bottom by 1 power, but it's not a p-series. It's not just 1 over n. Okay, so I'm going to use limit comparison with the harmonic series because the harmonic series is 1 over n. We know that the harmonic series diverges, so I know that this one's going to diverge as well. Okay, justification, that's going to be the limit comparison test. So, first step, I know it's bigger on bottom by 1, so I'm going to compare it to the harmonic series. So I'm going to start by saying the sum from n equals 1 to infinity of 1 over n diverges. No justification necessary. Everyone accepts that the harmonic series diverges. Okay, now I'm going to compute the limit of the ratio of the terms. The limit as n approaches infinity of 4n divided by n squared plus 1 divided by 1 over n. So that's going to be like multiplying by n. Wait, I said dividing by 1 over n, which is multiplying by n over 1. Okay, if you can see that this is 4n squared over n squared plus 1, and that limit's going to be 4, good for you. Write down 4. If you don't see it, actually distribute. Okay, 4n squared divided by n squared plus 1 multiplied by 1. Okay, this limit, okay, biggest thing I see is n squares on both of them, so this is going to come back 4 over 1. Okay, and pretty much if you're trying to do the limit comparison test and you're not getting an eats DC type situation, then you're doing the limit comparison test wrong. Because if it comes back 0 or infinity, which is what you would get if it was faster on bottom or faster on top, respectively, then the limit comparison test fails. You can't just say it's got the opposite behavior, unfortunately. Okay, and then so since this is, pardon me, I need to make a little remark that this is positive and finite. Okay, therefore, this has the same behavior as that. So, say, so the integral from 1 to infinity of 4n divided by n squared plus 1 also diverges. Okay, if the series S is formed by multiplying the nth term of A by 1 over 2n, write an expression using summation notation for S. Okay, so basically the nth term, okay, so maybe I'll say, you know, these things are an, and S equals the sum of bn. Okay. Bn is equal to this term here, this nth term of A, multiplied by 1 over 2n, okay, which is going to be 4n divided by 2n to the 3 plus 2n. Okay. And then we're going to determine whether this series converges. But I didn't actually do, well, maybe that would be good enough if I said it's the sum of bn and I gave bn. I don't know. I'm just going to, okay, n equals 1 to infinity of 4n divided by 2n cubed plus 2n to the first. Okay. And then we're going to determine whether S converges or diverges. Okay. S is going to converge because it's bigger on bottom by 2. So my plan is I'm going to do limit comparison with 1 over n squared. Okay, so first step is the sum of 1 over n squared, that converges. Why does it converge? Because it's a p-series with p greater than 1. Okay, so by p-series test, and I'm going to give a little more, p is equal to 2, which is greater than 1. Okay. Then I'm going to compute the limit as n approaches infinity of the ratio of the terms. Okay, the ratio of the terms of S is 4n over 2n cubed plus 2n. And then I'm dividing by 1 over n squared, which is multiplying by n squared over 1. And that's 4n to the 3 over 2n to the 3 plus 2n. That limit's going to be 4 over 2. Okay, that limit is positive and finite. Okay, so the limit comparison test works. So this series has the same behavior as that series, which is to say it also converges. So the sum from 1 to infinity, I could have written S here, but I already went too far, so I'm going to say it also converges. Okay, so that was a good limit comparison test problem. Okay, S is a geometric series right here. T over 1 plus t to the n. Find the value to which S converges when t is equal to 3. Okay, so I'm just going to start by plugging in t equals 3. I think that's going to be the thing to do. So 3 over 4 is going to be the thing inside the parentheses. So it's the sum from n equals 0 up to infinity of 3 over 4 to the nth power. All right. And then I'm going to say, all right, well, this is a geometric series. The common ratio is less than 1 in absolute value, so it's going to converge. You kind of already told me that. And so that's going to be equal to the first term. The first term is when n equals 0, so that's 3/4 to the 0 power, and that's going to be 1. Multiplied by 1 over 1 minus 3/4. Okay, that'd be a safe place to stop for free response, but for multiple choice, you know, we'd need to go a little farther. 1 times, well, 1 minus 3/4 is 1/4. 1 divided by 1/4 is 4. So I've got just converged to 4. Okay. Determine the values of t that make the series S converge. Okay, that's going to be an interesting problem because I'm interested in t divided by 1 plus t being between -1 and 1. And this is going to have some like interesting algebra consequences, I think. So I know that the absolute value of t over t plus 1, that needs to be less than 1. Okay, but that also, it's between -1 and 1. Okay, now I'm going to multiply all three sides of this inequality by t plus 1, which is fine as long as t plus 1 is positive. But there was nothing in there saying that t plus 1 had to be a positive number. So I have to split this up into two cases, right? So I'm going to multiply everything through by t plus 1. And what I'm going to do instead, or what I'm going to do is I'm going to say, all right, case 1. If t plus 1, obviously negative 1 is not going to work, right? T equals negative 1, that's not going to be useful to us, right? Because then I have negative 1 divided by 0, and that doesn't exist, so how can I take it to the nth power? So if t plus 1 is greater than 1, I don't really have to worry. I'll just multiply everything. So I'll have negative t minus 1, when I multiply that over there, is less than t plus 1. Okay? This inequality here is vacuous. It doesn't mean anything. T is always less than t plus 1, no matter what t is. So really all I have here is negative 1 is less than 2t. And that means t is greater than negative 1/2. Now I'd also been making the assumption that t plus 1 is greater than 0. Pardon me, not greater than 1. Okay, if it's positive and I multiply both sides of an inequality, it's not going to change the direction of the inequality. Okay, so t needs to be greater than negative 1 and t is greater than 1/2, so that's just t is greater than 1/2. Okay, that's some values of t, that's not all the values of t, right? I don't think, algebraically speaking, that they would ask you to do this, in 2022, but who knows? Okay, this is pretty intensive algebra. If t plus 1 is a negative number, then when I multiply all three sides of this by t plus 1, well, then I'm going to have to reverse the direction of the inequality. So I'll have, okay, negative t minus 1, okay, now I have to reverse that, is greater than t, which is greater than t plus 1. Okay, and again, we know t is always greater than t plus 1, so that's not telling me anything. So I've got 2t is less than, what? Huh. Oh, okay. So over here, I've got 2t is less than negative 1. T is, what is this? T is less than negative 1 over 2. But also t is less than negative 1, right? Because t plus 1 is negative. So if t is less than negative 1/2 and t is less than negative 1, well, that just means t is less than negative 1. Let me just look at what I got last year and just make sure that I'm not just like completely off, or I didn't neglect to think about something. What number is this? This is 6b. Yeah, well, I didn't even consider what happens if 1 plus t was negative. I did it last year. No, it wasn't last year, it was a couple of years ago. That was a huge mistake. Okay, so I think those are the values. I'm going to pause real quick and find the scoring guidelines just to make sure. Okay, yeah, I'm not exactly seeing it in the algebra or whatever, but this is just not contributing any solutions, because just like think of a number that's less than negative 1, like negative 2. Then you'd have negative 2 over negative 1 to the n, so it'd be like, negative, or 2 to the n. That's not going to converge, okay? So this is not contributing any solutions. It's somewhere in there in the algebra. I'm just not seeing it. I don't want to spend a whole bunch of time just staring at it. So it's just t greater than negative 1/2. For some reason, it didn't work. Okay, not sure really what it is. Find all values of t that make the sum of the series greater than 100. That's something we can do, okay? So the sum of the series, if it's geometric and it's converging, is going to be the first term times 1 over 1 minus, okay? Well, the first term is where n equals 0. Regardless of what this is, I'm going to be having 1 as my first term. Now, I'm assuming that we aren't interested in the sum of 0 to the n, but then that series won't be greater than 100. Okay? So what I'm going to do is I'm going to say, all right, first term, which was, let me wrong color, 1 times 1 over 1 minus the ratio, which was t over 1 plus t, that it needs to be greater than 100. Okay. And let's see. This is not going to be a negative number because I know that the absolute value of this is less than 1 for it to converge. So I don't have to worry about multiplying. Like when I get rid of this, I'm going to multiply it over there. I don't have to worry about that being less than 0, the denominator, so that it would reverse the direction of the inequality. So I'm going to say now that tells me that 1 is greater than 100 minus 100t divided by 1 plus t. Okay. So I'm going to subtract 100. Okay, I'm going to, okay, now that I know that t needs to be greater than negative half, I don't have to worry about multiplying this over here. So negative 99 minus 99t is greater than negative 100t. Add that over here, and I've got negative 99 is greater than negative t. Okay, so I know that it would be t less than 99. Yeah, oh, okay, it looks like that was not the original version of the question. Interesting. Oh, yeah, you can also simplify this. Okay, there was easier algebra to be done. I didn't think about putting these together with common denominators. I'm just going to attack it. Here, I'll show you something else. Okay, if I make this a common denominator, I would have 1 over, pardon me, 1 over, okay, 1 plus t over 1 plus t is going to be that 1 right there, minus the t over 1 plus t. Okay, and then that's going to be, well, that's just going to be 1 divided by 1 over 1 plus t, which is 1 plus t needs to be greater than 100, and so t is greater than 99. Wow, that was way easier. Pardon me. I just didn't see that. Didn't see that as an option. All right, let's move forward. That was enough of that. Okay, and I still got 2 more pages. All right. Let f be the function defined by f equals 3 over 2x squared minus 7x plus 5. Write an equation for the line tangent to the graph of f. Yeah, it's been a while, but I'm sure that'll be nice. All right, so point is going to be x equals 3. Y equals f of 3 is going to be 3 divided by 2 times 9 minus 7 times 3, 7, 14, 21, plus 5. Okay, negative 3 plus 5 is 2, so it's 3 halves. Okay, the slope. Okay. I was going to be like, what does this have to do with series? Okay, so I'm going to actually call this, just for now, probably not forever, but 3 times 2x squared minus 7x plus 5 to the negative first power. Okay, so that I can more easily take the derivative of it. Okay, the slope is going to be f prime of x equals negative 3 times that thing to the negative 2 multiplied by the derivative of that thing. Okay, I already computed that and found that it was 2, so I'm just going to be using that fact. Okay, when I plug in 3, f prime of 3 is equal to negative 3, 2 to the negative 2 times 12 minus 7 is 5. Okay, so that's going to be negative 15 divided by 4. Okay, so the equation, which I don't really have that much room for since I'm writing with a pretty thick pen here, it's going to be y minus the y-coordinate is equal to the slope times x minus the x-coordinate. Now we're going to find the x-coordinate of each critical point of f on the interval between 1 and 2.5. Classify each critical point as the location of a local maximum, local minimum, or a neither, and justify my answers. How many are there going to be? Okay. Who knows? All right, so I'm going to write out f prime of x as the fraction now. So it's going to be negative 3 times that 4x minus 7 divided by 2x squared minus 7x plus 5 squared. All right. If you can factor this, go ahead, right? Because we need to check all the critical points, which would be places where f prime equaled 0, which would come from zeros at the top, or was undefined, which would be zeros at the denominator. Okay, I'm trying to think, yeah, I think this one is factorable, and it's gonna be 2x minus 5 and x minus 1. You can either believe me on that, or, oh, and they're intentionally excluding those. Okay, if you don't see that, you're going to use the quadratic formula. Okay, so, and then I'm just going to work it, assuming you didn't know how to factor it. If you know how to factor this, go ahead. I just said what it is. You can do that. But I'm going to say, all right, for the bottom, x equals negative b plus or minus the square root of b squared minus 4 times a times c. Oh, that's convenient. All over 2a. Okay, that's also why it's factorable, is because this is a this thing is a perfect square. So it's 49 minus 40 is the square root of 9. And that's going to be 7 plus 3 over 4, so that's 10/4 or 2.5, or seven minus 3 over 4, which is equal to 1. Neither of those do I care about because they intentionally excluded those, it looks like. All out for nothing. And so really the only critical point that I'm interested in is this one, where the top is 0, and that's where x is equal to, well, 4x minus 7 equals 0, x equals 7 divided by 4. Okay. Now I'm going to be interested in if that is a relative maximum, relative minimum, or neither. Now, if you want to use the second derivative test, you can take the derivative of this. Doesn't look that fun. I think instead, I'm just going to test a point to the left and to the right of 7/4. Okay, so I'm going to try, and it won't be too bad because I know negative 3 is always negative. This is always positive, and, well, I can just test that. Okay, so at x equals 7/4 is 1.75, right? Yeah, 1 and 3/4 is 1.75. So I'm going to use x equals 1.5, and then on the other side I'm going to use x equals 2. X equals 1.5 gives me f prime equals a negative number, negative 3, times 4 times 1.5 is 6, minus 7 is another negative number. Well, yeah, sure. Divided by a squared number, which is going to be positive, provided it's not 0, but I know it's only 0 at places I'm not interested in, which is not 1.5. So that's positive. Okay, and then when x is equal to 2, on the other side of 7/4, I'm going to plug that in. I'm going to have 8 minus 7, f prime equals a negative number, negative 3, times 8 minus 7 is a positive number divided by a squared number, which is going to be positive, and that is negative. So since the derivative went from positive to negative at x equals 7/4, I know I'm at a maximum. Okay, so I'm going to say okay, there's a maximum at 7/4 because f prime goes from positive to negative. Okay, there's a sign change. All right, using that identity, evaluate the integral or show that it diverges. Okay, okay, cool. I was going to say, like, that still doesn't have anything to do with series, but then finally it has a series. All right, so what we're going to do is we're going to run the integral from 5 to infinity of 2 over 2x minus 5 minus 1 over x minus 1. whoops. Just realized I've been rolling this whole time. Alright, so this is going to be, I'm going to need an antiderivative. Alright, so that would be, it would be 2 log of the absolute value of 2x minus 5, but I'm going to have to divide by that 2 for the chain rule, so log the absolute value of 2x minus 5 minus 1 log of the absolute value of x minus 1. And if you're like, wait a second, where'd that 2 go? Take the derivative of this, right? You have 1 over 2x minus 5 times 2 for the chain rule. So the 2 is already like ready to go from here. Okay? And then I'm going to let this run from 5 to infinity. But actually, this is one of the rare cases where you're actually better off using that log property. So I'm going to say, okay, from 5 to infinity. But I could also say that this is equal to the natural log of 2x minus 5 divided by x minus 1 as x runs from 5 to infinity. So this is the limit as x approaches infinity of, all right, the log of 2x minus 5 over x minus 1, which is going to be the log of 2, right? As x goes to infinity, that fraction, okay, I don't have to worry about the absolute value because when x is going to infinity, it's definitely positive, and both of these things are positive. Okay, so this is going to be the log of 2 minus, when I plug in 5, I've got 10 minus 5 is 5 over 4. Okay, and so it's log of 2 minus log of 5/4. And if you really wanted to, you could call that the log of 8/5, I think, but no need, right? This is good enough. All right. Determine whether the series S defined below converges or diverges. State the conditions of the test used to determine that convergence or divergence. All right. Well, I'm going to... I got 2 options that I can see. One, I just did the integral test, right? I think that's probably what they wanted you to do. But also, I see it's second degree in the denominator. Okay, and I know that I'm like really fluent with the limit comparison test, so I guess I'll just do both of them for you. All right, with the integral test, I'll do that in blue. Okay. The integral test, I'm going to say f of x equals 3 divided by 2x squared minus 7x plus 5 is continuous, positive, and decreasing. Okay, that's the first, that's the condition. Okay. Then I just showed that the integral from 5 to infinity of 3 over 2x squared minus 7x plus 5 dx converges. Okay, therefore, the sum from 5 to infinity of 3 over 2n squared minus 7n plus 5 also converges. Okay, that's the integral test. But I can also do the limit comparison test, right? And so I'll just show you both of them. You've got both options. And you personally, you need to do whichever one you would think of first, right? I don't have an infinite amount of time here. Okay, whatever the first thing you think to do, go with that. And as long as it's, you know, right and reasonable. So this would be limit comparison. Okay. First step is pick a series to compare it to. 1 over n squared. So I'm going to say 1 over n squared converges, I might say from 5 to infinity. Doesn't matter what that lower bound is, as long as it's not 0. Okay, that converges by the p-series test. P is equal to 2, which is greater than 1. Okay, now I'm going to compute the limit. The limit as n goes to infinity of this divided by 1 over n squared. Which is like multiplying by n squared over 1. 3n squared over 2n squared, that's 3 halves. That is positive and finite. Okay. Therefore, I'm going to say, so the sum from 5 to infinity of 3 divided by 2n squared minus 7n plus 5 also is converging. Okay. Same conclusion, right? Two different ways. Okay. Determine whether the series converges or diverges using the p-series test. All right. All right. I think what I'm going to do for this one is I'm going to write out the general term. You see, that's not something that you have available to you here, right? So these are all p-series because it's like powers of 1, 2, 3, and so on. Powers of 1, powers of 2, powers of 3. We're just going to figure out what power we're talking about. This is 2 to the 1.5 power, right? 3 to the 1.5 power. So this is, okay, you could also call it 1 over n square root n. 1.5. Converges because p is equal to 3/2, which is greater than 1. Okay. Over here, I've got, looks like the third root of n divided by n to the third. Okay. Or, if I did the subtraction, that would be 3 minus a third. 3 is 9/3, so if I subtract a third, that's going to be okay. Pardon me, got distracted by an email. Or n1 over n to the 8/3. This is going to converge because p is equal to 8/3, which is bigger than 1. Okay. Root 2 over 2 is, well, it's root n divided by n. Okay. I could write that as n to the 1/2 divided by n, which is like 1 over n to the 1/2. Diverges because I've got p equals 1/2, which is less than or equal to 1. Okay. Now I've got some weird powers of 1, 2, and 3, but I know that that's okay. That's going to be my p. Okay, so p equals negative sine 4 divided by e. Or I guess it's going to be, the p is going to be positive sine 4 divided by e because the negative kicks it down into the denominator. Okay, so I'm going to say that 1 over n to the sine of 4 divided by e. Sine of 4 is a number that is between negative 1 and 1. I have no idea what it is. I think it's negative because 4 is bigger than pi, okay, and less than 2 pi. So it's going to be negative. Yeah, so it's actually going to go back up in the numerator, so it doesn't even have a chance to converge, right? Because it's bigger on top. P equals sine of 4 divided by e, which is certainly less than or equal to 1, because e is bigger than sine 4. I know that. Okay. All right. Keeping on going. Number 9. Okay, it looks like I'm coming close to the end. All right. Just the following statements about the convergence of this series is true. Direct comparison, I don't know. Well, you can't converge by comparison with 1 over n because 1 over n diverges. Okay. Sum of 1 over n squared, maybe. Let me think about this. Okay. You can't diverge by comparison with a convergence series. So I think it's gonna. I know what it is. Okay. It's going to be this one. It's going to be diverges by comparison with 1 over n. Okay, I can't do the limit comparison test, though, because if I divided this by that, I'd have an n in the numerator and a log of n in the denominator, and that would grow faster on top, and it would go to infinity. So I wouldn't have a finite and positive limit. So I'm going to have to do direct comparison. Okay. This is a tough multiple choice question here. All right, so really the question is 1 over log of n plus 1 greater than 1 over n? Because then that would show that it diverged because it was bigger than the harmonic series, which we already know adds up to infinity. Okay, so That's like asking, is the log of n plus 1 less than n? Which I feel like it is. How would I know that for sure? Yes. Okay. I'm going to take e to both sides power, and that will preserve the direction of the inequality. Okay. And starting at 1, is 2 less than e to the 1? Yes, bigger than 2. N equals 2. Is 3 less than e squared? E squared is between 4 and 9. So yeah, it's gonna work. Yes, that's always true. So I'm going to say it diverges by comparison. Okay, that one was a little difficult. Okay, determine whether the series converges or diverges, explain my reasoning. Okay, this one diverges by the nth term test, or by the divergence test, right? The limit of the terms is 3. So the more terms I add, I'm getting closer to adding 3 and 3 and 3 and 3, more 3s, and we know that's going to diverge. So okay, limit is non-zero. Okay. This one is bigger on bottom by 1 power, so I know it's going to diverge, and my reasoning is going to be the limit comparison test with the harmonic. Okay, so I'm going to say this one. Okay, I'm going to start on the limit comparison test. I'm going to say that the sum from 1 to infinity of 1 over n diverges because it's the harmonic series. I don't need to give a reason. We all accept that. Okay, now I'm going to compute the limit. Limit as n goes to infinity of 3n divided by n squared plus 2n divided by 1 over n, which is multiplying by n over 1, is 3n squared over n squared plus 2n. Okay, that limit is 3. Okay. And as a result, I'm going to have, all right, and pardon me, I need to say is positive and finite. And then right, limit comparison test, only good for showing that this thing does the exact same thing as what you have in mind. Okay, this one is going to converge because it's bigger on bottom by 2. So same process, 1 over n squared converges because it's a p series. Okay, p is equal to 2, which is bigger than 1. Okay, now I'll compute the limit. Limit as n approaches infinity of 3n to the 2 divided by n to the 4 plus 2n times n squared over 1, which is dividing by 1 over n squared. It's going to be 3 over 1. Okay, and that's positive and finite. Okay, therefore, I'm going to say the sum from 1 to infinity of 3n to the 2 divided by n to the 4 plus 2n also converges. Okay, and then this one. I think we talked a little bit about this one. I think that was in this lesson. Okay, yeah, we did limit comparison with a geometric series. Okay. What you want to do, just like over here, you kind of want to look at the overall biggest thing happening, and it's n squared over n to the 4. This one is 1 over 2 to the n. It's the biggest things I've got happening. So I'm going to compare it to 1 over 2 to the n, which is a convergent geometric series. Okay, so maybe I'll change the color because this one's going to be limit comparison, but it's going to be a little different, right? So I know that 1 over 2 to the n converges. It's geometric with r equals 1/2, absolute value of r less than 1. Okay. Now I'm going to compute the limit. Okay, and then this limit will be equal to 1 because, they're essentially the same, 2 to the n and 2 to the n. We would divide the coefficients. There's no really coefficient on 2 to the n. It's just 1 times 2 to the n, and 1 times 2 to the n is positive and finite.
So as a result, I'm going to say the sum from 1 to infinity of 1 over 2 to the n minus n also converges.
That's all for that problem set. Thanks for watching.